Okay, now let's work on the fun stuff. We want to be able to integrate in the complex plane. Integrating in the complex plane is similar to integrating in real analysis, except now, instead of working with a very basic idea of calculating the area under the curve, we aren't using that logic here. It's a bit more sophisticated, but because imaginary is abstract, if we just think of it in a theoretical way, we are able to talk about integration in a complex plane in the following way. Let's say we have a curve C in the complex plane where we go from some initial point to some endpoint. Now C is going to be, let's say for example, this curve right here. Now this curve will be represented by Z as a function of some parameter t, because we normally associate Z as a point. If we say now Z as a function of t, meaning that we take our parameter t that varies from some a value to some b value, we are able to cover an infinite amount of points to get from one endpoint, starting at our least value of t that we want, to our last endpoint, Z as a function of our last t value. So we would say that we have Z of t, and then we would say t would go from some value of a to some value of b, just like in real analysis. So then let's try to look at an example. Now, if we were to, well, let's first establish the idea of a complex valued function, so we get familiar with integrating in with complex numbers, that is. So let's add an integral from 1 to 2 of 3t plus I, and that's squared. Now, of course, we have dt. Now, t is our parameter again. I wanted to present this because now we have I here, but everything's still pretty much the same. Let's see what we get. We expand this out, so we get our integral from 1 to 2 of 9t squared. 3t times I gives us 3ti, but we have two of those, so we have plus 6ti. And of course, I squared is just minus 1, and that's dt. So when we take the antiderivative of each term, what do we get? We get 3t cubed plus 3ti minus t. Now, we go from where to where? 1 to 2. So to finish it off, we have 2 cubed, which is 8 times 3 gives us 24. 2 times 3 gives us 6, so we get 6i right there, and then we are subtracting 2, of course. Now, this is not 0, so we should be subtracting something in parentheses. Now, 1 to the power 3 is 3, so we get that. 3 times 1 is 3, so we get plus 3i, and we get minus 1 here. Now that subtraction side distributes over, so although we run out of space, we can just do this really quick in our head. We get 24 minus 3 plus 1, which gives us 22. I'm forgetting the minus 2 there, so actually let's just make that 20. And now that takes care of our real part. Now let's focus on our imaginary part. We have 6i here, and what else do we have in I? We have this 3i here, but that's being affected by that subtraction sign. So we have 6i minus 3i, and we get the grand total of 3i. So this is a complex valued function, and this will aid us in calculating line integrals in a complex plane when we actually get some curve C here. Here we didn't have a curve, but we will be able to look at examples that we are able to find the integral value for in complex integral traversing a curve C.